Today, the plan is to review several papers on multitask and transfer reinforcement learning. For the last paper for diversity is all you need, we'll have the author of the paper join us. For now, I am given a foreshadowing for his talk. So what are we talking about? What is multitask and transfer reinforcement learning? Where some settings, these are approaches that are used in some reinforcement learning settings where either the environment is parameterized or there are several possible goals that you can achieve. So in OpenAI there is actually this environment called this class called Goalenv, and it describes so all of the environments that we are going to be talking about today, the kinds of environments that we are going to be talking about today, they usually inherit from this class because they are environments where you can solve different tasks. So in the market decision process framework that we have been talking before, it has been just a single, we have had a single reward signal. So you are taking some actions in an environment, the environment changes, and you're getting your reward signal that tells you whether you're achieving the task or not. And the system doesn't really admit the idea that tasks can be different. Here, this in OpenAI, that's a special kind of environment that does admit the idea that you can work towards several different goals in the same environment. So they do it via this function compute reward with respect to goal. In the market decision process terms, ones we are familiar with, we can say that in a usual market decision process, we have a transition function. So probability of next state given current state and action. These are the dynamics of the environment, right? This is how it evolves given our actions. And we have a reward function. So now we are introducing a third piece of the puzzle. We are introducing environments that instead of one single reward function, have a goal-oriented reward function. And so your reward tells you the reward, what is it for? Its goal is to tell you whether you're achieving your task, whether you're achieving your goals. Well, the environments we have looked at before have been paternalistic environments that know what your goal is for you. Well, in this case, we are generalizing to understand the fact that different agents can have different goals, and we can be deciding what the goal is. The most simple example of it are geographical environments, different kind of labyrinths, where your goal is literally a place where you want to reach. The goal in such an environment is a vector of size 2 that represents a point in space that represents where you would like to go. And your reward is then how close you are to that goal. Your reward, it will probably be some kind of Euclidean distance from where you are to this goal. It doesn't take. So if you look at common tasks like robot tasks through this lens, through the lens of having potentially different goals, you understand that most, if not all, tasks in real life are like that. So for a robot, you can give very different directions towards what the robot has to do. A robot might have to come to a certain place in the environment, or the robot has to carry something from place to place, or the robot might have to break something or race other robots, and so on. So this is a more general. This is the more general way to look at tasks that doesn't separate tasks into completely independent silos. That tells you that we can have similar tasks in one environment. And then it's pretty clear that you shouldn't learn how to get to this goal, how to get to this goal, how to get to this goal. This shouldn't be three separate algorithms. So the algorithms that help you get into goal one probably share a lot in common with the algorithms that help you get into goal two, and the algorithms that help you get into goal three. So if you look at it through our old lens of just usual single task reinforcement learning, you would train a policy for coming to goal one, and then you would train a policy for coming to goal two, and then you would train a policy for coming to goal three. Which is obviously not very smart, because there are a lot. All of these policies will all have to learn common elements. They will have to learn how to go around corners, how to move, how to. If it's a walking robot, they will have to learn the walking algorithms. So there is a lot of overlap, and we are interested in multitask and transfer reinforcement learning. Is an area interested in jointly learning these tasks, in reusing some of the things we've learned in one task to solve another task. The difference between multitask and transfer reinforcement learning isn't that big. I would say that transfer learning is a subset of multitask, because multitask approach just means that we have some set of possible goals, like goal one. So there are many goals we can try to work towards. And transfer learning, it specifically refers to the case where we're learning to solve this and then we want to learn to achieve goal two, but without doing it completely from scratch. We want to reuse some of the knowledge that we have and some of the skills that we have from goal one to learn how to achieve goal two, and so on. So that's the only difference between terms. That's just a boring important part to so that we're on the same page about what words mean. And if you don't have any questions or comments or remarks at this point, I should remind that in these formats, we try to encourage any participation. So any comments you might have are welcome. Then let's move on to the first paper I wanted to talk about. This is a paper from DeepMind. It's called Universal Value Function Approximators. And there, the key in their approach to multitask reinforcement learning is creating this multitask value function. So just as a quick reminder, a value function represents how good a certain state is for achieving rewards. So its expected reward. A value function is expected reward after a certain state. If you are in state S, what is the expectation of the rewards you will get since this point towards the very end. They want to. So in traditional setting, you would have a value function for each goal, and they want to parameterize it in such a way that it depends on goal G. So it takes G as another input. And they have several approaches to this. So here we go. This picture represents most of the paper. So you have a certain state representation and a certain goal representation. This is something that comes from the environment. So S is whatever you observe in the environment. So when you're solving the tasks, we're not making any decisions on what S and G look like. S and G are part of the tasks; they're part of the world. And G is some vector definition of a goal, and that is a sort of weak link in this paper that they don't. So they say in all of their examples are environments where you. All of their examples are environments where your goal is a certain location. So you have to come to some place in a labyrinth, in a topology, and the agent can make certain moves in this environment. And so your goal is the coordinates of the location you want to go to. That's the most obvious way to define a goal. And the rest of the paper pretends like the goal isn't necessarily a location. The goal can be anything, but they don't expand on it. So theoretically, any goal that you can represent as a vector will work with their approach. But they have only looked at the low-hanging fruit, the most obvious thing to represent as a vector, which is a physical location. So they suggest three approaches to do this. Well, more like they suggest one. So this is the one they pick. Basically, they start with the left one, find faults in the left one, move on to a better one, and then move on to the additively, incrementally move on to this approach. So the first approach is the most obvious naive one. It is you have vector S, you have vector G, you can concatenate them and feed them into a neural network that would predict value function V. And that's it. That's a solution. This didn't work well enough, and in a minute I'll go deeper into why. So they then moved on to the second approach, is having a separate neural network for state and for goal. And then fitting this into the H function, they say that H function can be a lot of different things, but in their case, this is a cosine. So they've decided that, so they're saying that it generalizes to other H functions, but in all of their experiments, that was cosine. And what that means is that both the current state and the goal are mapped into the same space, and the value of your state is how similar it is to the goal, which is a reasonable idea, right? You can even do it with cosine without in a topological space where the goal is actually the coordinates of where you want to go to. You can actually do this without the neural networks. You can measure the distance between where you are and where you want to be, and that would be your value. But obviously, that doesn't take into account the complexity of the environment and that there are labyrinths and so on. And to take this complexity into account, you have these neural networks that maps them into different space. And the third approach is the same architecture, but it's trained into steps. They train separately these neural networks and the joint part. I will look at it in more details. Yeah, so this is the formula for actually training for what the value function should be, but it is no different from any other RL method. They're just so in the paper their contribution is just representing the V via these models, representing the V via the goal. So where would I? Yes, so the first two methods, other questions on the first two methods. So the way these two methods work. This is just one neural network that is trained like any other value function. And this is the pair of neural networks with a cosine in the end that you can just backprop in the same way, in the same manner. Yeah, right. And the third is a little bit more complicated. It is this two-stage process. And so what they notice is there is a trick in reinforcement learning where you replace parentheses with square brackets. I know it sounds not very academic, but this is the transition between tabular methods and neural methods. So in the basic RL course in the Sutton Bartow book, for example, they start with tabular methods where all of the states and all of the actions are discrete, and then the value of a state is not a function; it's a table. And you have state value of state 1 and value of state 2 and value of state 3 and so on. And then when you want to apply the methods that were created for the tabular approach, you want to apply them in a non-discrete environment, you replace the square brackets with round brackets, and you say that this is no longer a table, this is now a function. And we approximate this function via neural network. So in this vein, they have looked at value of state and goal. If you look at your data set, then it does become a table because you have collected, so your agent has behaved for some time, like have done some things in the environment. You have had your agent run around and collect data. And so now you have these trajectories. And a trajectory is this was my goal. This was my action. This was my state that I got into. This was my action. This was the next state, and so on. And it has rewards as well. Action, state, reward. So this is the trajectory. And so your agent has collected a number of these trajectories. So now your value over, so of course, the value function should be a function over all possible states S and states G. And they are continuous. So there is an infinite number of possible states S and possible states G. But in your data set, you only have a number of particular states and particular goals. So this becomes a matrix. So you have a matrix of S horizontally, G So you have G1, G2, G3, S1, S2, S3. And here you have the value of the second state for the third goal, or for the second goal. Okay, so we're 2-2. Okay, then if we look back onto our architecture, this second architecture, it is a cosine. Actually, I think they even simplified it further. So it's no longer a cosine, but it's just a dot product. So you don't normalize it. It's a dot product. So it's also a measure of similarity, right? You can measure similarity between two vectors by using dot product. Then this model means that value of state S for goal G equals phi of S dot product, this letter psi, I think it is, of G. Then if you look at the matrix, at this matrix, so here it is here we're looking at one example, but if we look at a data set of examples, like at the matrix, then essentially we get that the matrix V, where element VSG means the value of states as for goal G, because there is a finite number of states and goals for in our data set. This matrix equals matrix phi by matrix psi. So this is just a dot product. So if one element of the matrix, is a dot product of phi s and psi g, how do we represent this? How do we present this operation where every element of the matrix is a dot product of a row and the column of the matrices we have? This is a matrix multiplication. So this value table, that we have decomposes into matrix multiplication. And matrix decomposition, we're not going to look into it today deeply because our topic is RL, but it is a solved problem in mathematics, basically in linear algebra. There are a lot of methods for that. You can use SVD, singular value decomposition, to factorize any matrix. So this problem of we have matrix V, and we want to get two matrices that are a factorization of V. All we have to know about this problem now is that it's solved in mathematics. So we can first do this decomposition, and then we have a perfect data set for training these two neural networks, phi and psi. So we have a matrix of what phi and psi should be. We have now a data set of state, goal, and correct phi. State, goal, and correct psi. And then it's purely supervised learning from here. And this is in theory equivalent. So the second approach and the third approach are in theory equivalent, because these are two mathematically different ways to achieve the same, to optimize the same function. But the third works much faster and much better, and this is their contribution that really let them basically use this model and make this model usable. Ouch. Yeah, and so they have some interesting results. So you can see quality growing as it should. Yeah, and here they're also looking at generalization. They're looking at when we're trained on some. We have trained on some goals G. We have trained on some examples of where we might want to go, and they show that for other locations it works as well. So it generalized beyond the examples of G that we had in the source data set. All right. With that, I'd like to move on to the next paper. If you have any feedback on this one, feel free to jump in. Right. So that will. Hindsight experience replay. This is one of the most, one of the simplest, which is nice, I guess, after the previous paper, and one of the most efficient algorithms in multitask reinforcement learning. It is an algorithm. It is basically a modification of our basic RL algorithms, the one like DQN, DDPG, SDQN, like these sort of algorithms you can look up into a Sutton-Berthaud book, or if you take any library that implements basic reinforcement learning algorithms, they will be there. But all of these algorithms are meant for single task reinforcement learning. And hindsight experience replay is an adapter, basically. It is how you turn an algorithm for a single task reinforcement learning setting into an algorithm for multitask reinforcement learning. And the way you do it is when you collect, so first you collect trajectories, right? So you pick a goal, and your agent tries to solve this goal. So you have the behavior of the agent is determined by the policy function. Every algorithm does that. Each of these algorithms has a policy function. They train the policy function differently, but the policy function is a distribution of actions given the state, and this is what controls the agent. So you initialize it somehow randomly, doesn't matter, and the agent goes ahead and tries to, it is still, the weights are random, so it's still really bad at doing anything, but it tries to achieve goal G. So we sample a random goal G and make the agent try to achieve this goal. Now, the agent has collected a bunch of trajectories. Right? The whole point of running a stupid agent that can't do anything is to collect good trajectories that we can learn on. And then, if we were using any of these algorithms, it has to be an off-policy algorithms, because you can see that we first collect trajectories and then we learn on them. And so off-policy algorithms are the ones that can separate these two steps. They can learn on trajectories that are stored. And so we have, instead of doing what those algorithms would do, they would look at the rewards. So those algorithms would do this. They would look at the reward for the states and actions they did and save what was the reward. But we, in addition to that, so this is what those algorithms would do. But in addition to that, we will look at some other goals and collect and look at what the rewards were according to those goals. So maybe you have achieved during this step of like try to solve G, try to achieve. Maybe during this step, you have achieved some different goal. You haven't achieved what you were trying to achieve, but you have achieved a different goal, and that's something to learn on. And all of the single task algorithms miss out on that because they are only learning on the goal they're currently working with. And so this is a fix for that, that we will not only look at the reward for the goal that we were trying to achieve, we will also store the rewards for some other goals. And then there is this S function. It really depends on what your goal structure is like. Says that it might be too long. So the S function exists to speed up the process to avoid enumerating all goals. And if the goals are continuous, then it's impossible to enumerate all goals, obviously. So we definitely need this S function. And S function subsamples some of the goals, and then we can subsample them randomly. So we can look at some random goals. Have we achieved maybe them, maybe some of those? That's very similar, by the way. I think this algorithm should be called something like, San Francisco startup approach, because it tries to do something and then looks at what have we actually achieved. We probably achieved something else, so we should pivot to this something else. Right, so these are potential pivots. S function represents potential pivots. And so that really depends. The reason it's opaque, we don't sort of explain how this S function works, because it really depends on the particular environment. It can be a random sampling over all goals, but in geographical environments, the S function will probably just return this M means it will return the location you ended up on. So if the goal is a location and you have ended up in a certain location, you have achieved that goal, right? So whenever you have ended up, you have achieved that particular goal that you're standing on. And so in a geographical environment, the S function would just return the current spot you're standing at, because it is one of the possible goals. And so you haven't achieved the goal you were looking for, but you have learned how to achieve this particular goal. All right, and then we've added, instead of adding one transition to the data set, we add several for different goals. And then we train our algorithm on them. Here, like, it doesn't really explain anything because it depends on your algorithm. You can use any algorithm you can think of. So DQN is the simplest one. It has to be an algorithm that trains on the data set of transitions. So these are the transitions. We were in that state. We took that action. This was our goal. This was our reward. And it trains on this data set to predict what good transitions are. All right. And this way you can fit any of policy reinforcement learning algorithm to work in a goal environment and to train to achieve several goals simultaneously. Some of the most interesting results here, let's look at the video. Okay. I'll have to type it, I guess. Ouch. So here we are. And what's interesting here is that they they measure the quality of the algorithm on one go. So the result that they're looking for is being able to achieve one particular goal, not being able to achieve a range of possible goals. But training with this procedure, with this hindsight experience replay procedure, where you learn to achieve different goals, actually makes you better at achieving the one goal that you were looking for from the very beginning. So the part on the right is training directly to achieve one goal, and the part on the left is hindsight experience replay that trains to achieve different locations. Which sort of intuitively makes sense, right? If you have learned how to pick an object in a different place, you'll have an easy time transferring that into how to pick an object in another place. Yep, and they've done it on a real robot, of course, because they can. Okay, so hopefully I've convinced you that hindsight experience replay is a good idea. If you don't have any responses on that, let's move on to the next paper. So that one I wanted to skip because we don't have too much time. Yeah. This paper, also by DeepMind, it's called Progressive Neural Networks. And it is an approach, a universal approach to transfer learning. So it's not necessarily for reinforcement learning, but their goal was reinforcement learning. And all of their experiments were in reinforcement learning because that's sort of the environment when, I guess, this issue is the most pronounced, most clear that you definitely have to do transfer learning. And their approach is this. What they're proposing is this neural network architecture. So this part, look at this part of the architecture, that is a usual neural network for solving a task. Now, it depends on what task you're solving. If you have video, if you have an image as an input and you have to output a decision, then it's probably going to be a convolutional neural network that will handle the image. With text, it will be the recurrent neural network. It all depends. It can be a simple feed-forward neural network, but it is the architecture that is suited to your task, basically. And here as input, you just have whatever input exists in your world. So in the reinforcement learning world, that would be state, and in the output in the reinforcement learning world would be action probabilities. So this is how we train. I think they trained Q function this way. Let's check it. I think they represented the Q function, I believe. Yeah, because advantage actor critic. So they're using advantage actor critic and DQN. So they're using a Q. This is the Q function. So in the reinforcement learning environment, that would be Q of S and A. That would be then the Q vector. So that would output a vector of this is the quality of the first action. This is the quality of the second action, and so on. Is there a question? Yeah, in case of advantage actor critic, yeah, we get an action as a second input. So if actions are discrete, then we're doing this. And if actions are continuous, then we are adding a second. So in the continuous case, we have S and A as an input, and we have Q as output. Yeah, thank you. That's a good point. In A through C, it would be continuous. Sorry that I missed your question last time. Scholarly word. If you still have this question, then please point out which part it's about. Okay. Okay. Great. Then let's move on. Feel free to anyone else like to ask any questions in the comments. So this is what's important to know about this part is that it is if you look at a task and you solve it without progressive neural networks, you solve it the simple way. This is the architecture you would use. So you would usually use only the left part. This is the optimal neural network architecture for whatever task you're dealing with. Now, in this case, we want to then, so you've taken this architecture and you've learned how to solve the task. Then we are interested in learning how to solve a different task. And here's where it becomes interesting. So the traditional approach would be to maybe you take, if you want to do transfer learning, you take these neural networks that you have learned, and you then fine-tune it. So you start with these weights, and you fine-tune it to the new goal. The problem with this approach that they're addressing in this paper is catastrophic forgetting. So if you do it with a lot of tasks, you want to learn to solve 15 tasks, and you learn to solve one, and then you take this neural network with these weights and fine-tune it for the second, and then you continue training it for the third and for the fourth, and so on. The training that the neural network that you're training for task number 15 doesn't really contain any information about task one. So this procedure of train for G1, then train for G2, and this procedure where you sequentially optimize weights for different tasks, it really fades quickly. So it remembers only a couple of last tasks. Its memory fades like it really can remember only a couple of the last ones. It's very similar to the problem that you have in recurrent neural networks, that they are also looking for architectures that let you carry on a lot of more information from the beginning of the sequence, because naive architectures can only carry on information from the last few elements. And the same problem exists in this scenario. Jordi, I think your microphone is on, and we hear you sometimes. Thanks. Yeah, and so you here we also are interested in avoiding catastrophic forgetting, and we create a solution that's also similar to what they created in the recurrent neural network. So instead of fine-tuning this neural network, you train a new one, but at each layer of your new neural network, it can look not only at its own previous vector, but also it looks at the previous vector of the last neural network. Right. So this is the formula for one layer of a neural network. You take what previous layer has output and multiply by a weight matrix. So if we added a parenthesis here, that would be the usual neural network. But instead, we add another weight matrix multiplied by the previous neural network results, and another weight matrix multiplied by the previous, and so on till the very beginning. So at each layer, we're looking at the previous layer of every of the neural networks that we have, of each of the neural networks. And the advantage this gives us is that we sort of get the best of both worlds. We don't forget, we don't throw out anything that happened, anything that we have learned from the previous tasks, but we also do train a completely new architecture for a completely new network for our task. And it is trained solely to, our new architecture is trained solely to solve the new task. So the weights of all of the previous neural networks are fixed here, and we are only training new ones. And they compare then, they have this number of approaches that they're comparing. So it's the first baseline is that the neural network is not doing transfer learning. You're training directly on a transfer task. Then it looks a bit similar to a transformer. Kind of. There is something there. I agree. There is no attention mechanism, but yeah, there is an intersection. So yeah, the second baseline is we are training on one task, then we are fixing the weights. We're fixing these weights. So what is red and what is blue, I would ignore because this is a bad graph and red and blue doesn't actually mean anything. But what you have to look at is the dotted lines here. So what's in the solid lines gets trained, and what's in the dotted line, it's the weights that get fixed, get frozen during during training on the target task. So the dotted line means that the weights are frozen when training on the target task. And they compare this approach where they're really interested in, because this is something people do a lot actually. That you think that that would work decently because the first layers of your neural network are sort of some generic embedding of what the environment is like, and the last layer is probably responsible for the real decision making. And so this logic tells you that you should probably fix this part and retrain the last part for different tasks. But their experiments show that it doesn't work that well. The third approach is that you train everything on one task and then on the other. So you don't freeze any weights. The third approach is an approach where you first initialize randomly. So your source task is, instead of the source task, you get a random neural network. instead of training on the source task, you get a random neural network, and then you train on the target task, and you use the progressive neural networks architecture. Then you use progressive neural network architecture the way God intended. First train on the source tasks, then on the target task, then treat this as two source tasks, and train on the third target task, and so on. These are their results so they're training it on, in this experiment, they're training it on Pong Soup. This is several versions of the Pong game. So some of them are dark, some of them are bright, some of them are, so they have noisy, black, white, and zoom. And then they have vertically flipped version, horizontally flipped version. So they have this zoo of very similar Pong games. And that's, I guess that's an easy experiment. That's an easy task because the games are pretty much the same. But you can see anyway that transfer learning is very useful. So this measure, 0 to 2, this measure is a transfer score. This is the score. This is the score after. Basically, this is the score with transfer learning divided by the score without. And whatever is green means that transfer learning has helped. And whatever is really deep green, like these parts, they are the parts where transfer learning made a 2x improvement on just training on the target tasks. So it's better to say source toward target divided by just target. And then they've tried it on a harder task where you are actually training on different Atari games. And does it help to transfer knowledge from one Atari game to another? And as it turns out, it actually does. They have some cheeky details here. I think they picked the report results over the best 3 out of 25 solutions or something like that. So there is some hyperparameter shenanigans going on, but it's still impressive, and it is. You would expect that at least some visual. So it proves that some visual functions of the convolutional neural networks can be transferred from one Atari game to another. And so you that are probably the parts that are responsible for understanding the environment, understanding what's going on the screen, can be transferred from one game to another. And here, for some reason, this game called Robotank really benefits from pre-training on other games. And the game called Boxing really benefits from pre-training on other games. So I guess this also reflects the way people play Atari games, because you also get better at the whole skill and not just at particular games. All right. I think that's all I wanted to say about it. Feel free to jump in. For the next things we're going to discuss is this paper. It's called "Diversity is All You Need," and I expect Benjamin to join us and present firsthand knowledge. I'm not sure. Are you with us at the moment? I don't think so. I think he's not here yet. So yeah, let's. If we don't have any discussion left of those papers, then let's have a short break, 5 to 10 minutes, and hopefully Benjamin shows up. Can we use Hindsight Experience Replay for continuous action environments? Yes, we can. Why not? There is nothing that prevents us. Let's see how. So. I mean, there is no requirement there of actions being. Yeah, definitely not DQN. You have to, but see, it works with N of policy RL algorithm A, and this RL algorithms can be A3C, for example, and it will work just fine. There is nothing in there that requires discrete action space. If you're interested in the more practical side of it, how do you actually do it? I can recommend stable baselines. You know this library, stable baselines 3. In stable baselines, no, that's GitHub. I wanted to see their docs. They implement these algorithms. So A to C, DDPG, DQN, Hindsight Experience Replay, PPO, Soft Actor Critic, and TD3. And all of these algorithms are compatible with Hindsight Experience Replay. You have to pick one, and you then supply HUR replay buffer to your algorithm of choice, and it should just work out of the box. And yeah. But it has to, so if you're using Hindsight Experience Replay, it has to be a goal env. So it has to be use the OpenAI Gym interface for an environment with a goal, because the usual OpenAI Gym interface doesn't know anything about goals.